So today, remember what we were doing? We were introducing these two important infinite dimensional vector spaces. Okay? So two important infinite dimensional vector spaces. Tongjia, you're new. I actually will send the lecture notes to you, so if you want to just watch, that's okay. Basically, everything I say is in these lecture notes. So two important infinite dimensional vector spaces. First one is little L2, right? And this was, as you recall, is the sort of two-sided sequences. Right? So you've got sequences of numbers going to negative infinity and positive infinity, and we require that the sum of the moduli squared is finite. Okay. And this was, remember that this is in the sense of the when we're talking about this two-sided limit, what we mean is that the limit of the partial sums from negative and positive n as n goes to infinity. Right? That we're taking a symmetric sum in both directions. Okay? Because that's how we're taking our sums of the Fourier series. Okay. And so this thing, right, we defined on it, so really not just vector spaces, but these guys are going to be inner product spaces. So we define the inner product was if you have two sequences, A n and B n, let's call the first one A and the second one B, then we define the inner product to be the sum of A n, B n conjugate when they equals infinity. Okay, and then we define the norm. Right, the norm of A was then the norm that you get from the inner product by taking the inner product against itself and then square. Okay, this is all old hat. So the only thing that we need to worry about slightly is to ask, is this actually a vector space? Right? Is it closed under, addition, vector addition, and is it closed under scalar multiplication? The scalar multiplication is easy. Is it closed? So is it true that is it closed under vector addition? Is it closed under vector addition? Well, that's the question. If we've got these two sequences and they're both in L2Z, if you sum them, are they still in L2Z? Right? So you've got these two sequences, A and B. Is A plus B not infinite? Okay, and right, that is, we need to show that that the limit as n goes to infinity of these guys with n goes to negative and positive n is fine. Right?
Yeah. This is the first example in the book, and the question I had, so I see that they're showing this vector space,
Yes.
to be answered, and then towards the bottom, they show the Cauchy-Schwarz holes.
Yeah.
That's not necessary for a vector space. Does that have to do with the basis, that we have orthonormal bases? Why do we show Cauchy-Schwarz holes? Is that necessary for a vector space, or is?
No, that's not part of being a vector space.
So what's that? What is the purpose of showing
so I have to say that it's a little bit peculiar to me as well that he proves first this thing to be an inner product space.
Because you want to show that it is closed under addition.
That's true. Yeah.
So
So
you
that's the
Cauchy-Schwarz
article
was
verse.
closed under addition? The Cauchy-Schwarz shows it?
No. Yeah. In order to show that this is closed under addition, we need a Cauchy-Schwarz.
Oh, that has to hold for it to be closed under addition?
well, what we're going to use here is the triangle inequality.
Yeah.
Right? We use the triangle inequality. So it's actually not clear to me why you need to prove Cauchy-Schwarz, because so here's what boggles me a little bit. If you look, remember last time we showed that if you have a vector space and it's an inner product space, then Cauchy-Schwarz follows, right? So my own question is, and I was gonna raise this, but was there anything about that proof that we did last time that relied on the space being finite dimensional? Because this is infinite dimensional. I looked through it. It doesn't look to me that there's any reason why we need to reprove Cauchy-Schwarz once we've got that this thing is an inner product space. But maybe take a look at it and see if there's something about it that's about that last proof that relies on it being finite dimensional. Again, I don't see it. So it seems to me that Stein says something slightly illogical here, and he's going to do it again in the next example when he proves Cauchy-Schwarz again for the next infinite dimensional space. So the only thing I can think of is maybe the proof doesn't work for the infinite dimensional space. So, but I don't see. I myself don't even see where the proof fails. So I must be missing something. If I figure it out, I will tell you. But for now, let's just go on and for some reason, no knowing Stein, we will prove these things which, at least in the finite dimensional case, are simply consequences of the infinite product. Okay. So we need to show that this limit is finite, and what we're going to do is we're basically just going to use we'll just basically use the finite dimensional triangle inequality. So, by the finite dimensional, yes. So triangle inequality. Yeah, I should say that there was another point earlier that I was a little bit confused about when Stein did something, which I thought he did not do. I'm not going to mention it. I'll let you guys try and figure out where it was that Stein did something which seems like he didn't need to do.
In today's lecture?
Not in today's lecture. It was in convolutions. That's the head. It was in convolutions. Okay. So in any case, this thing we can get easily by the finite dimensional triangle inequality, right? We know that this guy is bounded by and then you just take limits, right? So take the limit on both sides, and it's infinity, and then you get that that this thing, right? And this thing, of course, is smaller than this, and then you do so, which is finite. It's finite, and so that's basically all you need to show that this thing is finite. And then,
if A is 3, B is 5, and 64 bigger than 25.
if A, so I must 2 is on the right-hand side, yeah. Let me think for a second. So if you've got A plus B, right? Either A is bigger or B is bigger, right? So we know that this thing is smaller than 2A plus
If we use the norm to expand it, the inner product of the A and plus B, we're missing like the 2 times the real term on the right-hand side. Isn't there like a second of the inner product between A and B, and it'll be 2 times the good part? Is that what
yeah.
it says?
Hold on a second. So this should follow a finite dimensional guide, right? Sorry. You're right, I lost it. Let's see if we can fix it. Thank you. So this thing here, right, from negative n square rooted, sorry, right? This thing is the finite dimensional size of a truncated a n plus b n truncated at n, right? Okay, and so we know, let's not be so reckless, we know that there should be square roots here, right? That this should be, just by the finite dimensional triangle quality, this should be smaller than that, plus that. Right? Which is, this thing here is summation a n squared and half plus b n squared. Sorry. Negative. Sorry. Right? I forgot the square roots. Right? But now I get it. This is at least true. Okay. So, right, and each of these guys is bounded above by their individual, the norm of the infinite sum, right? Because you're just adding on more positive terms, right? And so we know that this thing is finite. Thank you. Save us from saying something completely wrong. Okay, so that thing is, so this thing is finite, and so we are in vector space, right? And simultaneously, you notice that, taking the limit of this gives you the triangle equality for the space. If you don't trust that the other proof was 3 dimensions. Okay, and it turned out, of course, it turns out that this space is really important for us, right? That this little L2, actually in some sense, embodies everything about all the information in the Fourier series. Right? Okay, so an important definition, which we so here's an important definition. If you have an inner product space, with a strictly positive definite, strictly positive definite inner product, which is further complete with respect to the metric induced by the resulting norm is called a Hilbert space. right? And it turns out that little L2z is an open space. The second example, the second infinite dimensional inner product space that we're going to introduce, R, it will not be a Hilbert space for a couple of reasons. The more important one being that it won't be complete with respect to the metric. There's sort of like a minor reason that the inner product is not strictly positive definite, that one can sort of get out of very easily. But the more important one that can't be escaped is that this thing is not complete. So R, so example number 2, the important infinite dimensional inner product space is going to be the complex valued Riemann integral functions on the circle that satisfy that satisfies that this is finite. Now, what you should be complaining at this point, because I've introduced a condition that is already fulfilled. Right? This condition is actually not adding anything. If you're a Riemann integrable function, then you're a value function. Oh, this is going to be finite. Right? See, I didn't mean to say this, but I'm going to say it because this is the L2 condition. L2, this says that the L2, what's called the L2 norm, big L2 norm, is finite. And that's really what this R is supposed to be. It's really not just the you know what happens when you complete it with respect to the inner product is you get this thing called L2. Okay. Yeah, and in fact, so you have this thing. Right, you define an inner product on it. The inner product of two functions is the thing that gives rise to the L2 norm. Right? The norm is, of course, the inner product against itself, which you see is when I just erase the L2 norm. There should normally be put a little 2 here, but since we're not going to talk about any other norms for these functions, we're just going to erase the 2. Okay. And like I said, there's trouble because, for one, you could have f being 0, right? You could have f being 0 even though the function f is non-zero, right? Even though the function f is not 0 in like on a set of measure 0. Okay. So the inner product is not strictly positive definite. Stein gives a proof of Cauchy-Schwarz inequality, sort of against what he was doing earlier. He gives a proof of Cauchy-Schwarz inequality. I think it's a sort of cute proof. You may know that the Cauchy-Schwarz inequality can be proved in 100 different ways. There's a book called The Cauchy-Schwarz master class or something. And the first exercise is figure out a proof of the Cauchy-Schwarz inequality. You just like figure out any proof of the Cauchy-Schwarz inequality on your own. Right? And then the rest of the book is like all these different ways of proving it. So just because there are a lot of proofs and it's kind of cool to see another one. I don't think I've seen this one. Yeah, it's going to be sort of different looking from the one we saw last time. So here what we do is we say, so let me show it to you. We use the fact that 2AB is less than or equal to a squared plus. Okay. So notice that this is true. That's certainly true. Okay. Then for any lambda, we see that, let me write the right-hand side first, that 1/2 of lambda, sorry, let me put it up here. You see that 1/2 of lambda 1 equals of f of x squared plus 1 over lambda minus d of x squared comes a half bigger than f of x d of x bar. Okay. So this is just sort of like clever choice of A and B. So you choose your A and B to get this thing. Okay. Okay. And then you notice, you say, well, look, then if we look at the absolute value of the inner product, well, that's going to be, you take the inner product, and move the absolute value inside by the triangle inequality, thing that's bigger, right? And now we use this thing above, right? And we end up with we end up with 1/2 of lambda times the norm of f squared plus lambda negative 1 times the norm of b squared. And then we take lambda to be norm of g and norm of f. And that gives you the Cauchy-Schwarz. So this is like just astonishingly clever way of proving the Cauchy-Schwarz equality. I'm afraid I don't have anything to say. Okay, so the next, what we're going to do now is we've actually already seen this before, but we're going to use the stuff that we've just said, right, to talk about Fourier series. Okay, so Fourier series in the language of infinite dimensional And once we link this to linear algebra, then we're going to start using results from linear algebra. Okay. So we have the Riemann integrable functions. As before, we've got the the inner product, etc. Right. This thing is an inner product space. Then we let E sub n theta be e to the I theta. Right. We see that these guys are an orthonormal set. These guys form an orthonormal set with respect to the inner product. Right. We notice, as we actually already did, that the Fourier coefficient, the nth Fourier coefficient, well, that's just the inner product of f against the nth element of this orthonormal set. Right. The inner product. That's exactly the definition of the Fourier coefficient. Right? And so if we rewrite, we can write the partial sum. Right? The partial sum, well, we were writing it, we can write it like this, right? It would be f comma en. So that we've already sort of seen before. Okay. And now we make now that we're linking this very directly to linear algebra, let's make a few linear algebraic observations, sort of pretty simple ones, but they'll be useful in getting to the main goal, which is to show that the partial sums converge to f with this norm, okay, with the norm induced by this inner product. So the way you want to think about this, right, is that you've got this norm. Right? The norm of something is f, the inner product of f against itself, the square root, right? And then you can define a distance, right? Being the norm of the difference. The trouble is that this is sort of like doesn't really satisfy the rules of the distance, because you could have functions who differ by on a set of values 0 and whose distance from each other is 0. Right? So it's not. This isn't really a distance. There's something a bit wrong with it. But you think of it like a distance. Okay. And what we're going to see is that although the Fourier series, as we've been hinting all along, doesn't allow you to recover your function in the pointwise sense, it will allow you to recover it with the sense of this distance. That is, the distance between the partial sum and the Fourier series will go to 0. So you recover it. This is all about recovering the Fourier series. Recovers that in L2. Let me erase this, go backwards. Okay. To get this, we're going to use some simple observations from linear algebra. First, and you should sort of sneer or laugh when I put these things up. First is that f minus the partial sum, okay, f en n, n, orthogonal to the n for all n less than n, of course, right? Because we've subtracted off the part. Right? If you take if you take this against a non-to-abuse notation, right? If you take this against some ek, well, what are you going to get? You're going to get 0. Okay. Second, well, since it's orthogonal, right, and you recognize this thing, this is so then if we write f as f minus the partial sum plus the partial sum, right, then this thing, we've broken it up into orthogonal pieces, right? This thing is orthogonal to this thing, right? These are orthogonal. And so, by the Pythagorean theorem, we know that this is true. By the Pythagorean theorem. Which who knows is which we're just going to write it like this: a sub n squared, where a sub n are the nth Fourier coefficients. But a sub n. Anyone confused? Easy so far? Okay. Okay. So now notice part 3. Notice given any C sub n, D sub n with n less than or equal to n. If we look at f minus summation of this C sub n guy, what we get is f minus s minus the partial sum guy, plus, for the same reasons, right? A sub n minus C sub n, D sub n. Sort of running through, running through the same sort of argument, right? We've got, we've just thrown in the, we throw in the partial sum guy, and we recognize that this is orthogonal to this, and we subtract it here again. Right? Everyone okay? The same reasons. So we running through the same argument. We get this. Okay. But what does it say? This says that the best thing that can happen is that if the A sub n's and the C sub n's are all equal to each other, right? The best thing that can happen is if, right? This is like, right? Says that the best thing that can happen, right? The smallest error the smallest that the difference between f and a combination where you're using the guys between negative capital N and positive N, the smallest area you're going to get is when all the C sub n's are actually A sub n's, right? In other words, the smallest error is when this is the partial Fourier sum, partial sum Fourier series. Okay. So right. So the point is that in this sense, the S of n is the best approximation in the L2 sense of f using linear combinations or via linear combinations of the n from n negative n to positive n. Right? The distance from you take some approximation of f. You say maybe this will be a good approximation of f. Okay, and you check the distance between that and f. Right? This is the distance. What's the distance squared? That's okay. You look at the distance, and we say, well, look, the distance is going to be, it's going to be this number plus something, right? And that something is, this number is unavoidable. This number is unavoidable. We can't make it any smaller, right? This number, if we toggle the C's, the best we can do is to take all the Cn's equal to A sub n's. Then this will be 0, right? And so what we see is that the error is smallest when this is SNF. So this is the best approximation. And actually, this is got nothing to do with partial sums. Got nothing to do with Fourier series. It's really a statement about what the normal base is, right? Like this sort of best approximation. It's just saying that the best approximation is the one that where you take the coefficients that arise from the orthonormal basis. So it's really just a linear algebra statement. Okay. So this is all stuff that you should have seen in linear algebra. Did you see this in linear algebra? Who did not see this in linear algebra? Who did not see this? Raise your hands, I want to know. Okay, so most of you did not see it. Okay, but this last thing will be the key. This last thing will be really key. Now that I've taught linear algebra, I don't know how many times. I don't know how many times. I think the best linear algebra book is a one by Leon, and it's called Linear Algebra. But yeah, this book I think is sort of a good comment. So it's not a super theoretical linear algebra book. So like if you want the good super theoretical linear algebra book, that's Thomas's book. And it's not called linear algebra. It's called non-dimensional. This is like the classic for super theoretical linear algebra. I don't think there's a matrix in the book. No, I think there are three. Like in one of the problems, there are three matrices. Now outside of it, there are no matrices. There are no numbers. There are no numbers. Outside of those numbers in those matrices. And maybe the problem numbers. So that's like a super theoretical book with which I was introduced to linear algebra. so you would use this book if you were sure that everyone was going to be a math major. This is the book that you would use. But if not, then you would use this book. Anyway. So best approximation, that will be key to the theorem, which is the main theorem for this chapter. If f is an integral function on a circle, and that's it, then the partial sum if you look at you see what this is, right? We square root, right? This is the L2 norm of the difference, right? The distance between the function and the partial sum in the L2 sense goes to 0. So, it may not be good if you're thinking about pointwise stuff, but in the L2 sense, the Fourier series is perfect. Right? It recovers the function exactly. It becomes the function in the L2 sense. Okay. Okay, and the proof is actually surprisingly easy. Does anyone know? Did you guys read the proof? Can somebody tell me how the proof goes? It's actually almost completely trivial.
They do it twice. So like a brief overview first, they do it for continuous, and then they do it for integral functions. And
so what's the key? What's the key in the continuous case? There's one thing you need to say. You approximate the function, right? So let's take in the case. Let's say that G be continuous.
Is this the second part where we assume, or this is the first part we just like not assume G? Don't be bound.
So let f be a continuous function, right? We want to show that the Fourier series is a good approximation of it, right? So what we do is we use, here's the key, use the Weierstrass approximation theorem. Right? Weierstrass approximation theorem says you can get a sequence of trigonometric polynomials that approximate this guy uniformly, right? So you can choose a trigonometric polynomial such that, let's call it P, such that right, the distance of f to P everywhere is controlled by epsilon. Right? And in that case, right, the distance in the L2 sense between f and p, well, that's also epsilon. Right? We get 1/2 pi, 0 to pi, absolute value of f minus p of x, dx squared, and half, and then the epsilon, as you see, just pulls out. Now, and then we use the best approximation statement. By the best approximation statement, we know that we see that taking This works because you can express the trigonometric polynomials in terms of the East-events.
East-events, right?
Yeah, in terms of that orthogonal. In terms of
They have to be orthogonal. So I guess we could make them orthogonal if they want. I mean, because to get the best approximation, don't they have to be equal to that?
yes.
And so then, did we show this for infinite dimensional then? I know it's true for finite, right? I mean, this holds an infinite dimensional. Is that this proof? Does this hold an infinite dimensional space?
I mean, it holds. I'm not.
Is it true? With,
It's what true?
if we have an infinite dimensional basis for the trigonometric polynomials, do we assume that?
But we don't.
We don't even need it.
I mean, we don't need that, right? Right? Because the trigonometric polynomial is finite. It has a finite degree.
Oh, right. Okay. Yes.
It's a finite degree.
Yeah.
Right? And so it's going to be approximable by some combination of the East-events. Right? Okay. Well, then take the n to be whatever degree is necessary to capture that p. Right? And then you know that S of n approximates it even better than that. Okay. So you know that the distance from here to here is smaller than this. So if the function is continuous, you're good. And then if the function is not continuous, if f is merely integrable, well then use the L1 approximation lemma. Use the L1 approximation lemma to get a g continuous with the same bound b same. Right? Same bound as f, such that the distance in the L1 sense between f and g is smaller than e squared over 2b. It's going to be one, it will not take me more than 1 minute to finish. Then, the distance in the L2 sense between f and g, the distance in the L2 sense, f minus g, well, we can bound one of these guys, right? F minus g is smaller than 2b, so we can pull that 2b out. Right? We pull one of the f minus g's. We bound one of the f minus g's by 2b. We pull that out. And we see what we have here. We've got the L, right? We've got the L1 norm, right? Well, this thing, like this thing here, as we just said, is smaller than epsilon squared over 2b. Right? And so we can square root of the epsilon. So, and then the same reasoning, right? So then we get a we get a trigonometric polynomial approximating g, right? So choose trigonometric polynomial approximating g, where the distance from g to p is smaller than epsilon, right? And then we see the distance from f to p is smaller than 2 epsilon, right? And the distance from f to p is smaller than smaller than 2 epsilon. And by the same reasoning, when we choose the s of n of the appropriate n, that I will be within 2 epsilon also. So the proof is actually pretty simple. well, in the continuous case, it's obvious. And then in the non-continuous case, you approximate by something. You use the L1 approximation lemma to get something close. And that's close to the Fourier series. Okay, that's it for today.